All right, here we go. We're going to run through how to do some calculations when we are titrating a strong acid, weak base. This is pretty much, not pretty much, this is the problem from the problem set. And so if you're working through your problem set, just kind of follow along. This is the strong acid, weak base one. I believe it's actually number 3 on your problem set. So the first thing, you're given this information that we are titrating, it's 50 milliliters of 1 molar ammonia, that's NH3, and you're given the Kb value there. We'll note that for later, is titrated with 1 molar HCl. And so what we need to first calculate is what is the initial pH? In other words, what is the pH of that 1 molar ammonia solution? So initial pH NH3 is a weak base, so I can write out kind of the base ionization process. So this weak base, NH3, will react with water to produce, it's a weak base, bases accept hydrogen, so we make NH4 and hydroxide. And this is essentially a equilibrium problem, so I think a Rice table is appropriate. We know the initial concentration of the ammonia is 1 molar. I don't care about the water. Initially, you've got none of the products. The change, we lose from the reactant side, gain on the product side. Lose X amount, gain X amount. For this one, we can assume that X is small because if you go back to what the Kb value is, Kb is a very small number, 1.8 times 10 to the minus 5th. And so since Kb is small, I can assume that we're not losing much from the reactant side. And so what I'm going to do is I'm going to write out my Kb expression. Kb is equal to the concentration of the products over concentration of the reactant, right? And now I'm just going to substitute and solve for X. So I know Kb is 1.8 times 10 to the minus 5th. The ammonium ion is X, the hydroxide ion is X, so X times X is X squared. We said that the amount that's lost is negligible, so I got my equation, 1.8 times 10 to the minus 5th equals X squared over 1. If I solve for X, I got that X is equal to 0.00424. And consequently, that is the concentration of the hydroxide ion. X equals the concentration of the hydroxide. And now, if I want to know pH, well, I have hydroxide ion concentration, so I can find POH. POH is equal to negative log of that hydroxide ion concentration. So negative log of 0.00424 I got that POH is equal to, we'll write it over here, 2.37. And if you remember, pH plus POH is always equal to 14. Therefore, pH is equal to 11.6. If I'm rounding to 3 significant figures. So, step 1 is done. I know the initial concentration of the ammonia, and I can use that to calculate the pH. All right, now we're going to go ahead and do part B. I want to know what is the pH after we've added 25 milliliters of HCl. And so I'm going to do, I'll just kind of write this out, 25 milliliters of 1 molar HCl has been added. So what is the pH? Well, this one is kind of a stoichiometry problem, really. And so here, I'm going to start with what is the acid-base neutralization reaction. So we have our weak base, ammonia, plus our strong acid, HCl. When these react, we're going to get the ammonium ion and the chloride ion. Right? Based on the concentration and the volume of the NH3, I should be able to figure out how many moles of NH3. And that's simply molarity is equal to moles divided by liters. We know the molarity of NH3. We know the volume. The volume here is 0.05 liters. And so we should be able to find the number of moles pretty easily. And since this is 1, this means that I have 0.05 moles of NH3 initially. I can do the same kind of thing for HCl. And so I have 25 milliliters of 1 molar HCl. And all I got to do on my equation is change this to 25 milliliters, which means I have 0.025 moles of HCl. Initially, I've got none of this, right? So then we got to kind of think about what's happening in our titration. The HCl gets used up, it reacts with the NH3. And how much reacts? These react in a 1-to-1 ratio. Those are the coefficients in the balanced equation. So all of the HCl is used up. We use up 0.025 moles of the NH3, which means that we are left with 0.025 moles of NH3. Okay. Also, we know that the amount of product is also in a 1-to-1 ratio. So if we use up 0.025 moles of HCl, that means we're going to produce 0.025 moles of ammonia. And we don't really care about the chloride ion. It's a spectator, but we'd also make the same amount. So here we've got no HCl left. We've now made 0.025 moles of the NH4. And again, we don't really care about the chlorine, but that's how much we've made, right? These are not concentrations, but we can make them concentrations pretty easily because we know the total volume. If we started with 50 milliliters and we added 25 milliliters, the total volume would be 0.075 liters. And that would be the same for all of these. Right? Which means that we can find the concentration. And what I would like to point out here is that the concentration of NH3 is equal to the concentration of NH4 plus. The fact that those two concentrations becomes important because if I look back to my Kb expression, I have NH3 and NH4 in my Kb expression such that those two quantities cancel each other out. And so I'm just rewriting that Kb expression from before. If, which it is the case here, NH3 and NH4 are equal to one another, those actually cancel out in that Kb expression. So Kb is equal to the hydroxide ion concentration, which that ends up making our math really pretty easy because, like we said before, we actually know Kb in this case. Kb is 1.8 times 10 to the minus fifth, which means our hydroxide ion concentration is 1.8 times 10 to the minus fifth, which means, once again, if you know hydroxide ion concentration, you can find POH. So POH in this case, I got 4.74, which means that pH is equal to 9.26. And I would like to point out that this just happens to be what we call the half equivalence point. So that's an important note that at the half equivalence point, the concentration of the weak base is equal to the concentration of its conjugate acid, which makes our calculation actually a little bit easier. So that's part B. All right, now we're going to take a look at part C. Part C is in our titration after we've added 50 milliliters of 1 molar HCl. I would like to point out that this is the equivalence point. How do I know that? Well, remember we were actually titrating 50 milliliters of 1 molar NH3. So just by looking at this, if you have the same volume and the same concentration, you have the same number of moles. So you've got the same number of moles of HCl as you started with for moles of NH3. So that by definition is the equivalence point. And so this titration, I'm going to again write out the titration reaction. We had NH3 and HCl. When these neutralize, we get the ammonium ion and the chloride ion. And as I mentioned, these we can use the molarity equation in order to get the number of moles of HCl, and likewise the number of moles of NH3. And so I know our molarity is 1 molar. Our volume, 50 milliliters, is 0.05 liters. And so I know the number of moles of ammonia, and the number of moles of hydrochloric acid is 0.05. And that's important because now we know that we're at that 1-to-1 ratio. So every bit of ammonia has reacted with every bit of HCl. So all of the HCl has been used up. All of the ammonia has been used up. So we've got no ammonia left. We've got no HCl left. Whatever we use from the reactant side, we gain on the product side. So we've gained 0.05 moles of NH4, and we've also gained 0.05 moles of chlorine, but again, this one's a spectator ion, so we don't really care about it, which means that at this equivalence point, if I have 0.05 moles of ammonia, I can find the concentration of the ammonia. And concentration is simply the number of moles in the total volume. And so you had 50 milliliters and another 50 milliliters. So the total volume here is 0.1 liters. 100 milliliters or 0.1 liters. So what I've done is calculated the concentration of the NH4 plus. So what that equals to 0.5 molar, right? And again, that 0.5 molar is ultimately going to be what determines the pH. And so I'm actually going to have to clear some space on my board. Remember this number, 0.5 molar NH4 plus. That's our concentration. This, I should also point out, is a conjugate acid, right? So if you have a conjugate acid in solution, that conjugate acid tends to want to get rid of its extra hydrogen. Where is that extra hydrogen going to go? It's going to go to a water molecule. And so let's show that reaction. So at equivalence, I've got this NH4 plus with water. It's in solution, so there's plenty of water around. This NH4 plus conjugate acid, so it's going to give its hydrogen ion away, make NH3 and the hydronium ion. The hydronium ion is going to be what causes the acidity of this solution at the equivalence point. Remember, we got our initial concentration of that NH4 plus just a second ago. That was 0.5 molar. Water doesn't count. We've got none of those product molecules at the initial condition. We can find the equilibrium concentrations by knowing we lose from the reactant side, we gain on the product side. So this is going to end up being 0.5 minus X. This is X amount, this is X amount. Hopefully this is looking familiar to you now, that we've done enough of these that you can kind of see the pattern here. I can write a KB expression for this. Actually, no, I can't, because this is a conjugate acid. We had already said that. So you actually write what we call a Ka expression. Ka for this reaction is over NH4 plus. So we've got our Ka expression. Now here's the catch on this. In this problem, you were actually not given the value of Ka. And so it would be impossible to solve this if you don't have the value of Ka. What you need is you need to use Kw to find Ka. Kw is equal to Ka times Kb. And we know Kw because it's always the same. It's the autoionization of water. By the way, this number, I believe, is given on the AP reference sheet. And this problem gave us Kb, so that was 1.8 times 10 to the minus 5th power, which means when I solve for Ka, I got 5.55 times 10 to the minus 10th for Ka. And now if I know Ka, I can substitute into my expression, and I'll be able to solve for x. Once I've solved for x, I know the hydronium ion concentration. Well, that's going to be how I get pH. So I'll go ahead and substitute and then solve. And again, as we've done many times now, we use the x is small assumption in order to make our calculation a heck of a lot easier. So instead of doing 0.5 minus x, I'm just going to do 0.5, which means that x is equal to, when I crunched the numbers, I got 1.67 times 10 to the minus 5th power. And that's my concentration of hydronium ion. And so if you've got your concentration of hydronium, you've got your concentration of hydrogen, and hence you can find pH. Remember, pH is negative log of the hydrogen ion concentration. Hydrogen and hydronium are equivalent to one another, and so I got pH is equal to when I crunched that number, 4.77. There it is. Okay, here it is, the last part of this problem. We are going to calculate the pH after we've added 75 milliliters of hydrochloric acid. And so this is past the equivalence point. So I've got 75 milliliters of 1 molar HCl added to, again, we started with 50 milliliters of 1 molar NH3. We can calculate the pH at this point. And so I'm going to write out that acid-base titration reaction one more time. Started with ammonia, added HCl to it, made the ammonium ion, that's NH4+, and the chloride ion, right? Recall from before that we started with 0.05 moles of this ammonium, and the way that I got that is simply molarity times volume equals the number of moles, right? That's our molarity equation. And here we've got 75 milliliters of 1 molar HCl, which means we've got 0.075 moles of HCl. And again, that's the molarity equation. Molarity times volume ends up being equal to the number of moles. And then we need to think about stoichiometry, right? These react in a 1-to-1 ratio. So now I have excess HCl. The NH3 is limiting. The most you can possibly use up is 0.05 moles. Right? So if I've used up 0.05 moles of each reactant. That means I'm left with no ammonium, and I'm left with 0.025 moles of HCl. And by the way, over here, we would have produced 0.05 of each of these, which means we've got 0.05 moles of the ammonium ions and 0.05 moles of the chloride ions. And again, we don't really care about those chloride ions because they don't do anything in terms of the pH. If we want to find the pH now, we've got to consider what is causing the acidity of the solution. There are two potential sources of the acidity. Now we have leftover strong acid, HCl. We got 0.025 moles of it. We also have produced some of this weak conjugate acid. That conjugate acid, we've produced 0.05 moles of that. And so we kind of have to ask ourselves, what's going to be most important in terms of the pH? Well, this is a strong acid, this is a weak acid, and so the strong acid ends up being much more important in terms of contributing to the pH of the solution. So the strong acid determines pH. Right? And that's because it sort of overwhelms the weak acid. It's kind of the big guy versus the little guy, right? And so this 0.05 moles of NH4 does not contribute significantly to the pH. And so we can actually simply calculate the concentration of HCl now. If I know the concentration of HCl, I'll be able to determine the pH. The concentration is simply moles divided by liters. The number of moles we just found. And we have to remember the total volume. This is 75 milliliters of HCl added to 50 milliliters of the solution that we started with, which means my total volume is 125 milliliters, or 0.125 liters, which means my concentration of HCl is 0.2 molar, which, once again, we know that strong acids completely dissociate, so the concentration of the strong acid is equal to the concentration of hydrogen ions. And if we know the concentration of hydrogen ions, we should be able to determine the pH. And so I'm going to calculate that pH then just by taking negative log of hydrogen ion concentration, negative log of 0.2 is equal to 0.07. In other words, this is a very acidic solution as a result of that excess hydrogen or that excess HCl in solution. So I hope this was helpful taking a look at these problems. Obviously, if you have questions, ask during class and we'll go over any questions you've got.